Hello everyone, Mr. Waz here, and welcome to another episode of WasleyScience. In this episode, we are going to be talking about climatology, and I'll be honest, I've been avoiding making this video for several years because it is controversial. You know, climate change and the impacts of climate change and why it's happening is still controversial in 2019. So I decided that I'm going to really stick to the facts here and what's going on and show you data. I wanted to start this episode, though, with sort of a story about myself. When I was a kid growing up in the 90s, everyone loved watching cartoons. We were very into the cartoons, and that's because there were just so many of them, from Cartoon Network to Fox to Disney to Nickelodeon, you name it. And there was one cartoon that I absolutely loved that I think had this weird impact on me deciding what I wanted to do in my life. And this cartoon was called Captain Planet. And it was, looking back at it now, it was quite a ridiculous cartoon. It was these kids from all around the world that had these magical rains that would shoot out elements, you know, earth, fire, wind, water, and heart. And when they, I don't know why heart was an element, but I don't know, it made sense at the time. Anyway, they would combine their rains and make this flying blue dude named Captain Planet, and he would stop the bad guys. In the show, the bad guys were these very transparent polluters that would tell everyone what exactly they were doing, why they were doing it, and they would say how much they don't care about the planet, and they would be trashing the planet in order to make profit, or honestly, they were just doing it for fun. And looking back at the show now, the issue is it's not exactly that there's protagonists and antagonists when it comes to climate change. We're all part of it because as a society, we demand electricity, we demand transportation, we demand globalization over having things local. What we need to do is go, okay, this is what's going on to our climate. Where do we go from here? So I hope that this video helps you understand what is happening to our climate, so that we as a society can say, okay, let's lay out our solutions so that we can promote sustainability. In this episode, I'm going to focus on 6 topics. I'm going to get into the difference between weather and climate just to get that established. I'm going to get into the greenhouse effect, factors that can influence the climate, the relationship between CO2 and temperature, how scientists exactly collect this data, and then last, I'm going to get into the effects of climate change. These are the NGSS DCIs that I'm covering in this video. We have 2 weather and climate ones about climate models and human activity, and then we have the 2 global climate change ones that talk about human impact and through simulations how we can look at the effects of climate change. One of my favorite things is in Connecticut when it snows and someone says, it's snowing, where's your global warming now? And that person just doesn't really understand the difference between weather and climate. It's why we make these 2 things a different unit in this class, is so that you can really see it. Now, climate is what you expect to happen, and weather is what you get. Weather's that short-term conditions in the atmosphere, temperature, precipitation, humidity, visibility, cloud coverage, all those things. Climate is when you take those things and you look at the average of a particular region over a long period of time. And we're talking like 30 years. And the climate usually stays relatively the same for thousands of years. And yes, the climate has naturally changed before. It's changed before there were humans. And usually when that happens, it's because of a positive feedback loop. And what we learned from our geologic time unit is when that happens, it usually leads to mass extinction. So that's why this is a really serious thing. So yeah, if it snows in Connecticut, it caused precipitation. No one ever said that it never was going to have precipitation in Connecticut again. In fact, Connecticut's going to be seeing increased amount of precipitation. We're going to see more rain, and of course there's going to be nights in which the temperature of the air is below 32 degrees Fahrenheit, so it's going to snow. So just because there's snow happening in Connecticut doesn't mean that global warming left. All right, so now we're going to get into the types of greenhouse gases. CO2 is the most common one, but there are other ones as well. I want you to make a table just like this, and I'm going to give you a couple different diagrams and pie charts in which you're going to need to take the different pie charts and diagrams and fill in the rest of this table. I gave you one example here with CO2. You're going to need a table with greenhouse gas, the chemical compound, the GWP, which stands for global warming potential, its major sources, its greenhouse effect to Earth itself, and then if there's like any other thing that's interesting that you want to jot down. Just note you're not going to get every single box filled in by the end of this. You don't have to do that. If you want to look at additional sources and pick up the gaps, you can, but it's not necessary. All right, so CO2 is a greenhouse gas. However, CO2 has some friends. So we have to talk about CO2's other greenhouse gases friends. And the reason for that is because they all come from different sources. Now, carbon dioxide is the most abundant by far of the greenhouse gases. There is also methane, nitrous oxide, which is N2O. And just to be noted, this is what can kind of get confusing. Nitrous oxide is different than nitrogen oxide. Nitrogen oxide is NO2, which is actually an air pollutant. Nitrous oxide is N2O, so two N's instead of two O's essentially. So we have nitrous oxide, and then there's nitrogen dioxide, which we talk a little bit about later in the year. And then you got these three other ones, which are part of fluorocarbons and hexafluorides. So the HFCs, the PFCs, and the SF6, these three are the least common. However, they are by far the most potent of the greenhouse gases, meaning they trap heat the best by far. And we're going to look at some numbers that are going to show how good they are at trapping heat. What I want you to see from here is that all these different greenhouse gases come from different sources. Carbon dioxide is the most abundant one because it's coming from transportation. It's coming from our cars. It's coming from power plants. It's coming from coal and oil, which are the things that we are doing the most. Methane comes from agriculture. It comes from natural gas systems because methane is natural gas. Natural gas is CH4. So all natural gas is CH4, which is a greenhouse gas. And it's also coming from landfills. So landfills release methane as the garbage is decomposing. Nitrous oxide comes out of cars as well, and it comes from fertilizers and manufacturing. And then our last three ones are the hydrofluorocarbons, the perfluorocarbons, and the sulfur hexafluorides. They're coming out of very specific manufacturer industries. So they're coming out when we're producing aluminum, when we're producing batteries, when we're producing semiconductors, all those type of things. So what this shows us is some of the greenhouse gases effect to the Earth. Now what you can see is a majority of this pie chart is carbon dioxide, which there's 394 parts per million in our atmosphere, and carbon dioxide together controls 56.4% of the overall global warming effect to Earth. If we take a look at the methane, which is the second biggest one, there's only 1.77 parts per million around the atmosphere. But with just that little amount, you compare the number 1.77 to 394, it still controls 16.3% of our global warming effect to Earth. So this little guy packs a punch. And we're going to see that more when we look at their GWPs, which again is their global warming potential. So the nitrous oxide, there's only 0.32, 5.4%. So the hot halocarbons are those two carbons that we were looking at before. And there's only 1 part per billion of them, but yet they can control a little over 10% of the global warming effect to Earth. And then there's ozone, which controls 10% of the greenhouse effect to Earth. This is ground level ozone. There's also ozone that exists in our stratosphere as well. I know that can get confusing. The chemical formula for ozone is O3, by the way, in case you need that. I have something to tell you. Water vapor is also a greenhouse gas, and a lot of people that deny climate change like to use this whole water vapor argument as something for them to say, hey, we never talk about water vapor. Why don't you ever talk about it? Well, here's why. it's not as relevant to the whole human activity climate change argument is because water in the atmosphere, or whether it's on land, part of the water cycle, is controlled by the amount of CO2 that's in the air. So the water cycle is dependent upon the carbon cycle. So if you pump more CO2 into the air, it's going to cause increased evaporation in some areas, and then as a result, increased precipitation in some areas. So yes, there's a lot more water vapor in the atmosphere. And yes, it's a greenhouse gas, but we're not adding water to the atmosphere. We're not like shooting it into the air out of like cannons that we got this water from. There's a finite amount of water really that exists on our planet. So that's the thing that's not changing. If you ever bump into other situations in which you are finding difficulty in sort of explaining climate change to somebody that denies it or does not understand it, I recommend you go to a website called Skeptical Science. When you go to Skeptical Science, you can see that they will list and categorize scientific literature about climate change based on the scientific myths that we get hit with, that we see in this discourse. So if you ever find yourself having to talk to somebody, check out that website, ask why they don't believe or why they deny climate change, find their argument, then click on that, and then show them the scientific literature that contradicts what their beliefs are. It's a really great way of enlightening people or educating people about the truth about this whole thing. So now let's move back to this left side here, the types of greenhouse gases. Finally, we can get to the GWP I've been telling you about, the global warming potential. And what we see here is that carbon dioxide, they use the number 1. Now, water vapor is not on here, but if it was, it would be some number less than 1 because water vapor is less potent of a greenhouse gas than carbon dioxide. And then we see methane, 25. What does that mean? That means that methane is 25 times more powerful than CO2. That means that it would take 25 carbon dioxide molecules to match up to 1 methane molecule. That's really important here. So now if we move down on this table, we can see nitrous oxide is almost 300 times as more powerful as CO2. That's what I keep saying. These other greenhouse gases pack quite a punch. Even though there are much fewer amount of them, they are much more powerful of a greenhouse gas. This is why we have to be concerned about all of the greenhouse gases that we are adding to our atmosphere, not just simply carbon dioxide. We can't just focus in on one of them. We really do have to look at all of them. Look at these hydrofluorocarbons. They're 14,000, 12,000 times more powerful, 22,000 times more powerful than the other greenhouse gases. That's just crazy. So we really have to look at the way that we're manufacturing things, the way that we're moving our cars, the way that we're running our agriculture. We have to do all of those in order to actually drop the amount of greenhouse gases to our atmosphere. So we just focused on the different greenhouse gases, and they have an overall influence on the Earth's global temperature. They can raise or lower it depending on how many of them are in the atmosphere. Now let's focus on factors that can influence the climate of a region. As you know, different environments around the world exist. You got the tundra, you got the grasslands, you got the deserts, you got the rainforests. So let's talk about what are the factors that can create those different environments. I'm going to focus on 7 of them for this. I'm going to focus on altitude, latitude, winds, ocean currents, nearby water, topography, and vegetation. So now let's dive deeper into each of these factors that influence the climate. First, we have the altitude. The higher the altitude, the lower the temperature. There are less molecular collisions the higher you go up a mountain, so it gets colder. This makes sense. We talked about this during the weather unit as well. Then there's latitude. I know you know this one. Areas that are closer to the equator are warmer because the sun is more direct to these places. They generally have like 12 hours of sunlight as opposed to experienced in seasons. The polar regions are the coolest areas. They have the most dramatic seasons. So if we look at this diagram on the bottom, you can see the area around the equator experiences the highest temperature. And then as you get farther away from the equator, it gets colder. So we know this one. Next, we have wind. So islands in areas that are western of continents have marine climates. They have warmer winds that collect the moisture and can enter colder areas and then condense. So there are the prevalent winds. So this diagram on the bottom shows like the main gist of how the winds on Earth move. And they move in that sort of curved matter there because of the Coriolis effect. Winds can have an influence of carrying warm air to colder areas. Then you have ocean currents. And speaking from an oceanography background, let me tell you that ocean currents are one of the biggest climate controllers of the world. Take Europe, for instance. Right? So Europe, if you look here, is like the same latitude as Russia. And you probably know this, Russia is cold, Europe not as cold. And the reason for this is you got that Gulf Stream current that's carrying warm water from the Caribbean all the way up to Europe, and it makes the entire Europe area warmer as a result. And Russia misses out on that. And it's a big deal. And if something happened to that Gulf Stream current, well, Europe will be as cold as Russia. So currents can have a way of transporting large amounts of heat from one location to another. So just being in the coastline as opposed to being really inland can have a major influence on your climate as well. Water, as we've learned, has a very high specific heat, and it can make a region more stable overall and see less differences in temperature. They can also have an influence on the wind patterns that are happening there. So if you live like in Old Saybrook, let's say, as opposed to West Hartford, Old Saybrook sees a smaller difference of temperature because it's right along Long Island Sound, so it has nearby water, and the water's high specific heat makes Old Saybrook see less of a difference of temperature throughout their day. And then we take where we live in West Hartford, and we see more of a difference of temperature throughout the day because there's less nearby water. Well, we're farther from the water. Now we get into topography, and just the presence of mountains nearby can have a major influence of what your climate is. So orographic lifting causes the windward side of a mountain to receive lots of rain, and then the leeward side receives small amounts of rain. So like you got California over here, and then over here you got Nevada. So California can get a lot of rain, which is why we like to grow all our stuff there. And then Nevada, we don't know what to do with it, so we plop Las Vegas. It's a desert, guys. That's what I'm trying to tell you here. Last, we have vegetation. So the amount of plants and trees on land can affect the amount of sunlight a region absorbs and stores. It can also hold the soil together and prevent desertification. So when we chop down a lot of our precious rainforest, it really opens the doors for that place's climate completely changing from this lush green area to a desert. And then it can spread from there. Having vegetation can also have a major influence on the overall climate of your area. It also can control the amount of moisture and humidity that's in the air because of evapotranspiration. All right, let's start to look at some temperature and CO2 data. We're going to be looking at a lot of it in class 2, stuff that's like much more updated than this, but I'm just giving you like the basic textbook situations that we're seeing. So the temperature of the Earth has been increasing about, if you take the overall average, it's just about to hit 1 degree Celsius or 1.4 degrees Fahrenheit. But the amount that is increased throughout the world is different depending on where you are. So what we overall see is that the temperature of the northern latitudes, like we're talking the Arctic area, has seen it the worst. They have increased a lot in temperature, a lot more than other places. And then if you go like lower in the latitudes, like closer to the equator, there has been an increase, but a smaller amount. So when we look at this average of almost 1 degree Celsius, we have to just realize that some areas are pulling the average up and some areas are pulling the average down a little bit. Even in the southern latitudes, they haven't seen as much as an increase as the northern latitudes. You have to remember that in the northern latitudes we have a lot more land, so the land is absorbing that extra temperature. So what we're looking at here is this is showing us temperature anomalies. Temperature anomalies is when the temperature is either hotter than it's normally been in that area or colder than it's normally been. That's why you're only seeing 3 degrees, 2 degrees, 1 degree, 0 degree, -1 and -2. So it's saying, hey, this region was 2 degrees lower than it normally was in 1929. Or this area was a couple degrees higher than it normally is. And when that normal comes from years and years and years of data of looking at the same day at the same time and collecting an average of what the temperature is of that particular latitude on the planet. So we can see here in the 1960s, it's colder in some areas, warmer in some areas. And then as we approach the 80s, that's actually when climate change was starting to become a thing that people talked about. And then we can see in the 90s, we're starting to see much more red than blue across the planet. But you can see how in the higher latitudes, especially in the Arctic area, they are seeing the biggest spike in temperature. If we look at carbon dioxide, we can see that the amount of carbon dioxide has also been increasing. So it's been increasing a lot. We're pretty much at 400 parts per million now in CO2 in the atmosphere, and it really hasn't been that much before. That's what is very frightening to a lot of scientists. And we've been recording it since the 50s with weather balloons, and it started out in Hawaii. They would basically release this balloon with a CO2 monitor on it, put it up in the atmosphere as high as they can get that balloon, and then they would chase it around in a Jeep and wait for it to come back down as the density would match, and then they would grab their CO2 monitor and bring it back to the lab and do this year after year. They did it for decades. And what is interesting about the amount of CO2 increasing is that it pretty much goes in exact sync with the amount of fossil fuels that we've been using. And that's where we make this whole humans using fossil fuels, CO2 going up, temperature going up. That's where we make the connection, is because they are all linked up together very nicely. We can see that we've been using more petroleum. Maybe we backed off on our coal a little bit, but now comes the natural gas. We've been seeing a lot more natural gas usage. And even as we make more cement for roads, sidewalks, foundations, that increases the amount of carbon that is in the atmosphere. And so here's the thing. It hasn't been like this before. The current CO2 level has never been this high. There's been points in our time in which crocodiles in tropical areas existed in Connecticut because it was so hot across the world. And the CO2 levels were not even that high then. So that's why this is such a serious thing, is that the current atmospheric CO2 levels are just absolutely off the charts. Okay, so this is like a very basic version of the hockey stick curve. The hockey stick curve is called this because when you look at temperature and CO2 over history, you see that yes, temperature goes up and yes, CO2 goes up a little bit, but recently it's gone up a lot. And so if you shifted this whole graph on its side, it would just look like a hockey stick. So this isn't exactly to show you data with this. This is just to get you with some terminology when it comes to climate change data. This is what we call the hockey stick curve. If you want better data than what I'm showing you on the video, here's a great website, climate.nasa.gov. And what's really cool is down here, it'll show you the current carbon dioxide levels, temperature levels, Arctic ice, ice sheets, sea level. You can scroll down here and it'll show you evidence of climate change, causes, effects, solutions. I'll just show you like what happens when you click on carbon dioxide, for example. It gives you an interactive graph in which you can hover over the slope and see when that was recorded. They have time lapses of every single variable here, so it's just a really great interactive graph. I highly recommend checking this website out. So let's take a look at all the cool ways that scientists collect data on climate change. One of the best ways I see is that they look into ice cores. So if we look up here, they drill into the ice and they'll collect this long cylinder of an ice core. And they do this in the Antarctic and as well as the Arctic, but they mostly do it in the Antarctic. And what you do is when you go deeper down into the ice, that ice became ice longer and longer time ago. The deeper you go, the older that ice is. And what they can do is they can look for bubbles in the ice, and they can take a syringe and pull that air that's inside that bubble out, and that air was the atmosphere tens of thousands of years ago. So then they can look inside that bubble and see what the CO2 levels were back then. So that's how we were able to get an idea of what amounts of carbon dioxide were in our atmosphere long before humans existed. Another way that we look is we can actually look at the rains on trees, that we can get an understanding judging by the space between each rain on a tree. That's your winter marks. We can have an idea of how much that area rained, and it can lead us to how much CO2 was in that area as well. We currently look at the CO2 in our levels with weather balloons still. We will attach a CO2 monitor to a balloon, let it go, and then find the balloon later and then see what the atmospheric CO2 levels are. For temperature, we love using our SST satellites. That stands for Sea Surface Temperature Satellites. And we've been doing this since the 60s. And it helps us get an understanding of the temperature all around the world, all the time, every single day. So this has helped us develop what is the normal temperature and what is an anomaly, meaning when is the temperature not like what it normally is. That's right, Roxy. If we look over here, we can see a sediment sample. So we can collect sediment samples on the bottom of a lake, and that can actually tell us what the CO2 levels were a long time ago. And last, we can take a look at documentation. We've been recording as long as we've been able to write what the temperatures were like and what the climate was like. So we can look back to the 1800s, 1700s, 1600s, even 1500s to get an understanding of how the climate has changed over the past hundreds of years. All right, so this is my attempt at getting every single effect of climate change on one single slide. Do you have to write all these down? Not really. You're going to be doing a project on a certain region of the United States, and you're going to look into what specific effects of climate change that place is happening. But here's all the ones I could possibly think of on one slide. Side effects of climate change may include melting of glaciers, decreased salinity in polar oceans, changes in ocean currents, melting of permafrost, thermal expansion of the ocean, sea level rise, increased flooding, increased precipitation, increased storm surges, frequency of hurricanes, severity of hurricanes, increased stress on clean water, ocean acidification, coral reef bleaching, desertification, migration of insects, changes of breeding seasons, extinctions of animals, increased algae blooms, increase in humidity, loss of soil moisture and soil erosion, droughts, heat waves, increased amount of wildfires, increased amount of waterborne diseases, food insecurities, increase in pest to crops, collapse of fishery industry, damage coastal tourism, and military conflict. We did it, guys. Yes! I gotta watch my favorite show here. Woo! Go for it, guys. You got this. All right, I got some videos for you here to enjoy. There's some on the greenhouse effect, some on climate change. So feel free to dive deeper down. Please remember to subscribe and take care. I got some stuff to watch.